Okay, so today we're continuing to talk about some general characteristics of polymers, including molecular weight distributions. We will definitely get to that today. I know we've been going a little bit slower than we planned on the syllabus. So we will get through that today, finish our discussion about polymers overall, and then hopefully get started talking about a couple of specific polymers. I've got a couple of them listed on the screen here. Some that are used commonly for medical devices, what those polymers look like, and why we would choose them for specific medical device applications. Okay, so we're going to talk about how we determine or how we calculate a polymer's molecular weight. And we're going to talk about how polymers are synthesized or put together. There are sort of two different reaction mechanisms that are used. They can be grouped into two different mechanisms. So we're going to talk about how that works. And then we're going to describe a couple of specific different polymers that are used for medical devices and talk about what the advantages of those specific polymers are for certain applications. So why would you maybe choose one material over another? Do a couple of review questions here. The first one is about the glass transition temperature, a concept we talked about last time. Okay, let me close the poll. Oh, answers are about evenly split for this question. Okay, good. So let's talk about this. So we talked about this concept of a glass transition temperature that is used to characterize or describe polymers, and it's distinct from a melting temperature. Melting temperature is associated with polymers that are crystalline or that have crystalline domains, semi-crystalline polymers. Polymers can be amorphous or crystalline. Amorphous is what we call them if they don't form those spherulites or those little crystals. And with any type of polymer, we can associate a glass transition temperature, which is a temperature where the polymer backbone starts to rotate and things can start to sort of spin around those carbon-carbon bonds in the backbone of the polymer chain. Accordingly, if we're able to spin things around those bonds, the polymer chains can start to slip past one another and slide past one another. Because if we're rotating things around the carbon-carbon bond, we're breaking the bonds between chains. The fact that they're able to rotate. So here in organic chemistry, it sort of drew a carbon backbone like this pattern. And at the glass transition temperature, we start to get rotation around these carbon-carbon bonds. And when you get rotation around those bonds, that tells you that you're breaking the associations, the secondary bonds, hydrogen bonds, dipole-dipole bonds between different polymer chains, which is what holds the whole polymer together. So at the glass transition temperature, when these things start rotating, we can start to see a change in the material properties of the polymer. We start to get deformation. And so this answer right here, B, is true. The elastic modulus or the stiffness of the polymer will be different above and below the glass transition temperature, because as these chains start to rotate, chains can start to slide past one another and we can get deformation. So at the same applied stress, we would get a different deformation, which means is another way of saying that the elastic modulus is lower above the glass transition temperature. Right, the polymer gets easier to deform above the glass transition temperature. Rahul asks if we're going to change the date of the midterm. We won't change the date of the midterm, but I'll change the content of what we're covering on there. Obviously, I'm not going to include content on the midterm that we've not covered in class yet. It'll only be what we've actually gotten through, what you have slides for, and what we've covered in class and homeworks. Okay, so answer B is true about the glass transition temperature. Let's look at answer C. Whoops, if I can draw an arrow. Glass transition temperature, or TG, is specific to a certain type of polymer. Because why? What does the glass transition temperature depend on? Or what are some things that make the glass transition temperature different? Does anyone remember?
It has to do with the structure of the molecule, because if it's like crystalline, that means it will be harder for it to turn into rubber. But if it's more amorphous and less structured, that means it's easier for the bonds to lose stiffness and become more flexible.
Yes, that's great. Yeah, so it depends on crystallinity. What determines the crystallinity of a polymer? Crystalline versus amorphous
The
characteristics.
structure of the patterns of the bond, whether if it's like a fixed or random.
What do you mean by fixed and random there?
If it's fixed, then that means structures go in a certain pattern. But if it's random, then that means there's no certain pattern of a structure.
Okay. So we talked about the tacticity of polymers, right? Whether the pendant groups are kind of on the same side of the chain or in a regular pattern off one side of the chain. Yes, that can determine crystallinity. Other thoughts? I see a chat message. Formation of spherulites. Yes, that goes along with crystallinity. So presence of spherulites. But thinking about the structure of the polymer itself, if we have polar pendant groups or side groups, functional groups, whatever you want to call them, on the chain, if they are polar, a lot of times that will promote secondary bonding between adjacent polymer chains. And anytime we're able to promote like bonding of polymer chains together or to one another, it's going to make the material stiffer. It's going to make it harder to deform. And when you're thinking about glass transition temperature, the more bonds you have between adjacent polymer chains and the more strong associations you have, the more energy you're going to need to put in to make it above that glass transition temperature. You need to break all those secondary bonds between chains in order to allow the backbone to rotate around the carbon-carbon bonds. Okay, so glass transition temperature depends on the tendency of the polymer to form spherulites or to be crystalline. The more crystalline the polymer, the higher the glass transition temperature. If you have polar side groups or functional groups on your backbone, that's going to also push you toward a higher glass transition temperature because you have to put in more energy to break the bonds between polymer chains. Bulkiness of, whoops, that's supposed to be a B. Bulkiness of the pendant groups. What effect does this have? Well, we want to think about the ability of polymer chains to pack closely together. So here's some polymer chains. They're next to each other in a polymer. What determines the spacing between these polymer chains? Well, if we have a bunch of bulky side groups off of our polymer chains, it's going to hinder their ability to pack closely together. So they're going to be spaced apart. So the bulkier those pendant groups or side chains, the farther apart polymer chains are going to be. And the easier it is, the easier it's going to be for those, actually the easier it's going to be for the polymers to remain entangled. You can think of polymer chains together as kind of like a bowl of spaghetti. And these bulky side groups or these pendant groups that are hanging off of the chain promote entanglement of the chain. So if you try to apply a stress or force to this polymer, if you've got no side groups, once you've broken any associations between the polymer chains, those polymer molecules are going to be able to slide past one another with relative ease. There's not really as much for the polymer chains to get stuck on, in other words. If, on the other hand, you have bulky side groups or you have these little side chains off of your polymer backbone and you apply the same force, the same stress to the polymer, there's a lot more places for those polymer chains to get caught on one another when you're trying to pull them apart. And so the effect that you see, that you observe on the macro scale, is that you can't deform the polymer as much. You don't get as much strain for the same applied stress. So that relates to glass transition temperature as well. If you've got bulky pendant groups, bulky functional groups on your molecule, that is going to affect the glass transition temperature and the ability of these bonds to rotate as well. Okay, so let's see here. Going back to the question, spending a little bit more time on this one because there was some confusion about the answer. So as the polymer is heated past its glass transition temperature, the polymer chains start to slide past one another. Yeah, this is actually, D is actually kind of the definition of what the glass transition temperature is. At the TG, we start to see rotation around the carbon-carbon bonds in the backbone, or maybe this is an oxygen. whoops, if you've got a siloxane molecule, as we talked about last time, this might be an oxygen here, so you would get rotation around the carbon-oxygen bond. That is what glass transition temperature is. So we are left with A here as the one that is incorrect. Below the glass transition temperature, the polymer is in a viscous liquid-like state. It's actually the opposite. So above glass transition temperature, the polymer is in a liquid-like state, right? Because above the glass transition temperature, we've broken that energy barrier that we need to start to cause a carbon-carbon bond rotation in the backbone to start to allow the chains to slide past one another and the overall polymer to deform. So are there any questions on this question? Or on this explanation, I should say. Someone asks, for bulky groups, are you saying the presence of bulky groups will increase TG or decrease? So the bulky groups, yeah, that can be a little bit confusing. So bulky groups tend to decrease the crystallinity and glass transition temperature are not, they don't exactly go hand in hand in every situation. So if you have bulky groups in your polymer, they promote less crystallinity. All right, they would promote more amorphous regions because the chains cannot pack as closely together as I've drawn over here. So bulky groups make your polymer less crystalline, but they would increase the glass transition temperature. And they increase the glass transition temperature because they promote tangling of the chains. They promote entanglement, which gives resistance to deformation when you apply a force. There we go. Okay, one more glass transition question. Okay. Great. So most of you answered C here, which is correct. The presence of bulky functional groups. Let me just write this down as a summary. Whoop. So bulky groups, they decrease crystallinity because what makes polymers crystalline is the ability of the chains to pack closely. And if you've got these bulky side groups, these chains can't pack together as well. They don't form as many crystals. They increase the glass transition temperature because they promote tangling of the chains, right? There's so many more places for these chains to get caught on if they have bulky functional groups, which makes the polymer not want to, the polymer chains not able to slide past one another as easily. So we have sort of an opposite effect here. Unlike with polar groups, if you've got polar groups, so just to compare and contrast real quick here, if you've got polar groups on your polymer chain, such as PVC, for example, polyvinyl chloride, if you've got chlorine, so here's two molecules, if you've got chlorine over here, everywhere else is hydrogens, you're going to get hydrogen bonding between the chlorine and hydrogens on adjacent polymer chains, for example. Here's all the hydrogen bonds. So that's going to promote the chains packing closely together, which is going to increase crystallinity, right? Chains close together means we're going to get more crystalline domains. It's also going to increase glass transition temperature because we've got more secondary bonds between these chains. So in the case of polar groups, the presence of polar groups increases both of these, crystallinity and glass transition temperature. But bulky groups is a little bit different. It can have different effects because while it makes the chains spaced farther apart, it promotes entanglement, which is what we care about with glass transition temperature, the polymer chains being able to slide past one another. Okay. Good. Hopefully that was a good review. Glass transition temperature can be a little confusing, a little tricky. Okay, let me get rid of this. It's blocking the screen. Okay, so another little recap here with a couple of pictures, things that affect the glass transition temperature. The bulkiness of functional groups will increase the TG, as we just talked about, because it's providing hindrance, steric hindrance, and promoting entanglement of the chains. If we've got polar chains, we've got more associations between adjacent polymer molecules, which makes it more difficult to slide those chains past one another. And it manifests as an increased glass transition temperature. So we can order these three polymers or these three monomers that you see here we can predict the relative glass transition temperature of these three compared to one another by knowing these the relationship of the bulkiness and the polarity to the glass transition transition temperature. Ooh, say that 3 times fast. All right, so moving on, we're going to talk about the molecular weight of polymers, and you'll see when we talk about polymer synthesis why this is the case. But polymers generally do not have the exact same molecular weight. We will talk about polymers as having a characteristic molecular weight, but it's really sort of an average. There's a whole distribution, like a bell curve of molecular weights in a polymer. And that's due to something called the degree of polymerization, which you can probably guess the definition of this. It means the number of monomers that have been put together in the polymer. If you put together 1,000 monomers in a polymer chain, the dP of that chain is 1,000. And so polymers have a distribution of molecular weights rather than just one. And we can classify this distribution 2 different ways. We have what's called a number averaged molecular weight, this first equation up here, or a weight averaged molecular weight. And let me grab my pen again, because this is a lot of things on the screen. These 2 equations here are the same. These 2 equations are the same. I just wrote them in a different way. Depending on the data, the way that you have data, you could use either of these equations and they would be equivalent. So here, let me grab a different color pen. Here, Ni is referring to the number of polymer molecules that have a certain molecular weight. That's what this I is here. So you'll get data, as you've probably seen on the homework. You have a certain number of polymer chains within a certain range of molecular weights. So here we've got the molecular weight of a polymer. I'll just put I, and then this is the probability or the frequency of having that molecular weight. So this would be the mean of the population, right? The mean molecular weight. So if we break this up into 5 bins or something like that, we've got, this would be I equals 1, I equals 2. We've got different molecular weight ranges, and we have a different number of polymer chains in each of those ranges. So here, the numerator, we've got the number of polymer chains within a certain molecular weight range times the average molecular weight in that range, average molecular weight of that range, over the total number of chains. So this is a weighted average of the molecular weight, but it's weighted by the number of chains of each polymer. Similarly, we can have a weight average function using the polymer's molecular weight rather than the number of chains. So just 2 different ways to think about the distribution of molecular weights in polymers. So this equation uses the number of chains and the average molecular weight. This equation uses what's called the mole fraction, which, if you remember from chemistry, we quantify the amount of a chemical in terms of moles. And so if you've got 20 moles in your polymer and 5 moles of it is from a certain molecular weight range, let's see, 5,000 to 7,500 grams per mole molecular weight, for example. The mole fraction of this molecular weight range would be 520 or 0.25. That's what we're talking about here with this xi. That's the molecular weight range. Sorry, that's the mole fraction. Wi here is the weight fraction, possibly more intuitive to understand. What's the weight? What's the fraction of weight coming from that bin of polymer compared to the overall weight of the polymer? So xi here is the mole fraction. Wi is the weight fraction, and you can use either of these equations to calculate the molecular weight distribution, depending on the data that you have. We can also calculate something called the polydispersity index. Polydisperse means that all the chains are, there's a distribution of chain lengths in the polymer. Monodisperse would mean that all the polymer chains are exactly the same length. So polydispersity index tells us how wide this curve is, basically. If you had, let's see, if you had two different populations here, one of your polymer samples had the distribution shown in red, another had the distribution shown in yellow. The red polymer sample would have a higher polydispersity index, a higher PDI, because this curve is wider here. It's more polydisperse. By contrast, the yellow polymer population is more monodisperse. Just some terminology, some vocabulary that we use to describe polymers. It's a little bit tricky because they don't have a set molecular weight like you would talk about for a metal or a ceramic. Okay, so whoops, the same slide here. Okay, so I have a brief example to show you. We have a polymer here that we have a little cartoon drawn of the polymer with a certain distribution of chain lengths. So we have two molecules of a polymer with 5 repeat units right here. This is the N5. 6 molecules with 10 monomers and 1 molecule with 15 monomers. And looks like each mer has a molecular weight of 2 Daltons. So we have a different associated molecular weight with each of these populations. And we're asked to calculate the molecular weight distribution, the number averaged and the weight averaged molecular weight. So I've copied the relevant information here. I'll be on the next slide. If I can get the slides to advance. Okay, so we're going to calculate the number average and the weight average molecular weight from the numbers that I gave you in the previous slide, which are right here. So the first thing we need, we're going to use these equations because this is the information we were given, right? We weren't given the information in mole fractions and weight fractions. We were just given the number of chains. So we'll calculate the numerator of this equation here, which is 170 Daltons. The numerator of this equation, you'll also notice, is the denominator of the weight average molecular weight. So we're going to use that number in 2 places. And then for the weight average molecular weight distribution, I'm going to calculate the weight fractions of the different components of the mixture. So the weight fraction of the polymer with 5 mers, we're going to take the weight of that polymer, which is 20 Daltons, and then the weight of all of the polymer chains put together, which is 170 Daltons, and calculate the fraction there. Similarly, we can do this for the polymer with 10 units, replacing the numerator, keeping the denominator the same, and for 15 units. So these 3 numbers, these 3 weight fraction numbers should add up to 1, because that's what we mean by a weight fraction. And they do. Okay, so we have the weight fraction now, and we've got the numerator and denominator. We can now calculate the number average molecular weight. So we've got the overall weight of the polymer divided by the number of chains that we have. So the average weight per chain using this method is 18.9 Daltons. And then taking these weight fractions again and using this equation, we can calculate the weight average molecular weight as 20.6 Daltons. So one thing you'll notice when you're doing these calculations, is that the number average molecular weight is always less than the weight averaged molecular weight, because the weight average molecular weight is a weighted function, and it's weighted more heavily towards, it's going to be more because you're taking the molecular weight of the polymer into account. So when you calculate the PDI is weight average molecular weight over number average molecular weight, it's always going to be greater than 1. And that's the case here. We have 20.6 divided by 18.9. So even though in your homework you were given data about the number, I think you have mole fraction in your homework problem, and the molecular weight ranges, you probably wouldn't be given the data in that format in the real world. but I'm having you calculate it just so you understand what these formulas are doing, and that we have a distribution of molecular weights in a polymer. But you can use various techniques called gel permeation chromatography and other techniques to get the molecular weight range of a polymer. So there are methods for calculating this. Generally, those methods are not going to tell you, hey, you have this mole fraction of polymer in this size range and this other mole fraction in this other size range. We would generally just get a number average or a weight average molecular weight from one of those techniques directly. But it's good practice to know how these are calculated and how we think about distributions of molecular weight in a polymer. Okay, so we can also do another super easy calculation for polymers, but it's useful to consider their properties, called the degree of polymerization. We can figure out the degree of polymerization by knowing what the average weight of the polymer, average molecular weight, and we use the number average molecular weight for this calculation, and the molecular weight of a monomer. So this basically tells us how many mers were put together to make this polymer chain, using the average length of a polymer chain. The higher the degree of polymerization, in general, the stronger the material is. So this, again, we were talking about how glass transition temperature relates to molecular weight. Higher the molecular weight, generally, the higher the glass transition temperature, because you have more spaces for the more chances for the polymer chains to tangle. The higher the degree of polymerization, generally higher melting point too, if you've got a crystalline material. It has a higher viscosity when you melt it, which makes sense when you think about the amount of energy you need to put in to break down all those bonds between polymer chains. So the degree of polymerization can tell us a little bit about the material properties as well. So if you see somewhere online, you know, you're looking up, oh, what's the elastic modulus of polyethylene, for example, or what's the viscosity of polyethylene glycol? It depends on the molecular weight of the polymer. It depends on the degree of polymerization. So I would caution you, especially when you're writing your paper, to not, there's not a single viscosity, there's not a single elastic modulus for a polymer. Those kind of things are always associated with a particular length of the chain, particular molecular weight, or a particular temperature in the case of elastic modulus. So be sure, if you're going to report those properties, to report under what conditions is that polymer, does it have that elastic modulus, or does it have that viscosity? So it's complicated, basically. So here's an example of how we might calculate the degree of polymerization. We want to find out the molecular weight of the repeat unit of the monomer. That's this little m here on the downstairs of this fraction. And so we would want to find out, we won't go through all these examples in class because we're running out of time, but you could calculate the molecular weight of each of these monomers using this table to the right here. So count up the number of carbons you have, multiply by 12, count up the number of other atoms you have, and multiply by however many you have of each of those. And I forgot to animate this slide, so it gave us the answer. We won't do this clicker question then as a clicker question, but we'll just work through it together here quickly. Okay, so we want to figure out the degree of polymerization of polystyrene with a number average molecular weight of 20,000. So again, that's the MN, number average molecular weight, 20,000 Daltons. Daltons is the same as grams per mole. It's the same unit. So to find out the degree of polymerization, we have number average molecular weight over the monomer weight. What is the weight of the monomer for polystyrene? Well, this is polystyrene right here. So it's a little bit hard to see with the transcriptions cutting us off at the bottom. But we've got this six carbon ring here. So we've got 6 carbons here and 2 on the backbone. So our, our monomer weight is going to be 6 times 12. That's the weight that we get from our carbons. And how many hydrogens do we have? If you go back to your organic chemistry class and think about how many hydrogens are on this ring, The circle inside this ring means we have sort of 1.5 bonds, not single bond, not double bond, 1.5 bonds inside this ring. So we actually only have 1 hydrogen off of each of these carbons. So there are 5 hydrogens on this ring, and then 6, 7, 8, 3 hydrogens on the backbone, 5 hydrogens on the ring. So we've got 8 hydrogens overall. Molecular weight of a hydrogen is 1. So we've got 72 plus 8. Did I do that right? 72 plus 8, 80. I think I messed something up. 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay. Oh, this is an 8. Sorry. This is an 8 here. 8 times 12, which is 96, plus 8, which is 104. So if you do the math here, it's going to equal roughly 192, which is answer C. So the degree of polymerization in this particular polymer, we're saying on average, there were 192 polystyrene monomers that got together to make the polymer in whatever sample this is that we're talking about. Okay. And the degree of polymerization depends on the reaction conditions, the catalyst that you're using, and so forth. So if you're a polymer chemist, you can try to formulate polymers to have a certain molecular weight distribution. You can try to make them more monodisperse. You can try to make the DP lower or higher depending on your needs. So using PEG as an example, polyethylene glycol, it's a polymer that's used in drug delivery applications, many other applications, probably a food additive too. Its physical state depends on its molecular weight. So a PEG that has a molecular weight of around 1,000 is going to be a liquid. A PEG with a molecular weight of 10,000 or more, it's usually called polyethylene oxide when it has a higher molecular weight, but it's going to be a solid. So the physical state of the polymer actually depends on its molecular weight, among other properties. As you can imagine, the stiffness, the viscosity, et cetera, depend on molecular weight. So typical molecular weights for biomedical applications would be in the range of tens of thousands to hundreds of thousands. One exception is one that we'll talk about kind of frequently in this class, ultra high molecular weight polyethylene. This is used for the cups of hip implants. That's kind of the most famous application of this polymer. And it's got a molecular weight of over 1 million. And it's a very stiff material, as you might suspect from its high molecular weight. It's very resistant to deformation and creep and all of those things, which is why it's a good choice of material for those cups and hip implants. Okay, so I wanted to talk about the polarity of polymer chains before we jump into talking about specific polymers and what they might be good for. So here I've illustrated 2 molecules of polyethylene. Polyethylene is the most boring polymer that you would ever want to see. All it is carbons and hydrogens here, single bonds everywhere. And as we know, the bonds aren't exactly at right angles or 90-degree angles as is drawn here. It's just easier for the sake of exercises like this to draw them this way. So you can kind of think in your mind that these polymers are not oriented this way, but this just lays it all out evenly so we can think about the relationships between different chains in a polymer. So we've got 2 molecules of polyethylene here. What kind of interaction or bond would you expect to see between these chains, if any?
Wouldn't you just experience like van der Waals forces between chains?
Yeah, exactly. Thank you. So there's going to be secondary bonds between these 2 polymer chains. And there's really there are no dipoles or anything here. So we might have some temporary attractions between these hydrogens or between hydrogen and a carbon of another chain. They would be characterized as van der Waals forces, very weak, very transient, but there may be some kind of interaction between these chains. Okay, these are non-polar monomers. So yeah, we're going to have weak secondary bonds between the chains and not a whole lot else. Let's see, clear these. Okay, now let's look instead at polyvinyl chloride, where we've got chlorine molecules off of the backbone. Now, what kind of interaction would you expect to see between adjacent polymer chains?
We'll see some dipole forces.
Yeah, dipoles, and specifically, because hydrogen is involved, probably hydrogen bonds is what we're going to see here. So the association between different molecules of PVC is going to be stronger than between different molecules of polyethylene. Polyethylene is a type of material that your plastic grocery bags are made of. Back when everyone had plastic grocery bags, you can still get them in some places. And as you know, those things tend to rip easily, usually when you've got a bunch of soup cans or glass jars or something loaded into them. They break pretty easily. Polyvinyl chloride, on the other hand, is a much stiffer material. It's used for pipes, like for plumbing, and for other applications that require something to be stiffer. So PVC and polyethylene, they really only differ. For some reason, the slide's not clearing. They really only differ in the polarity of the groups of the functional groups off of the backbone chain. One allows for hydrogen bonding, which is stronger secondary bonds. Polyethylene only allows for van der Waals forces, which are significantly weaker. And that determines the overall properties of the polymer. Okay, so there's one more classification scheme that I want to talk about with polymers, or some more vocabulary. Polymers can be classified as either thermoplastics, thermosets, or elastomers. And you can probably guess from just the name of these groups what each of these is. So, and I've illustrated, well, I didn't illustrate, I have this illustration on the slide that highlights the differences between a thermoplastic and a typical thermoset polymer. Thermoplastics, they can be linear or branched polymer molecules, and the chains tangle together, but they're not bonded together with primary bonds. So while you can have secondary bonds in a thermoplastic material, these chains they're just tangled, like ropes or like spaghetti strands. They're not bonded or associated to one another. So if we were to apply a tensile stress to this thermoplastic, these chains would be able to slide past one another if we apply enough force. By contrast, a thermoset material actually has primary bonds between chains. Let's see, between chains is what I mean here. Secondary bonds between chains. A thermoset has primary bonds between chains. So it's much harder to deform. If we apply a force to a thermoset material, it might deform elastically a little bit and then spring back. But we're going to ultimately have to input a lot more force, a lot more stress to get the chains to slide past one another or the polymer to deform, because we've got primary bonds holding the chains together. So you may want a thermoplastic or a thermoset depending on the application that you are pursuing. Thermoplastics are very easy to manufacture. They can be melted and remelted, which also makes them easy to manufacture, but they can undergo creep. They yield at lower stresses and that sort of thing. So there are trade-offs here, as there always are in engineering. Thermosets are stronger materials, but they can be more difficult to melt. They can be more difficult to work with, rather, or manufacture. So there are some trade-offs there. Oops. And then the third type, or the third classification of polymers, is elastomers. And you can have elastomers. Elastomers can either be thermoplastic or thermosetting, having the same designation as I just talked about. Thermoplastic elastomer will just have secondary bonds between the chains, no permanent bonds. You might have hydrogen bonds or something like that. A thermoset elastomer will be cross-linked, so different polymer chains will be covalently bonded to one another. But an elastomer is a material that undergoes elastic deformation. It's basically a rubber, is another term you can think of to describe a polymer classified as an elastomer. And thermoplastic elastomers are going to have the same properties as regular thermoplastics. They're going to be easier to process, easier to manufacture, and they're going to have elastic behavior. So you can classify something as thermoplastic, thermosetting, or elastomeric, and then elastomers can be classified as being either more thermoplastic or more thermosetting. So it's good to be aware of what type of polymer you need for a particular application, and then choose a polymer that fits those needs based on some of these designations. You might need something that undergoes a lot of strain, for instance, or you may not want your polymer to undergo elastic strain at all. Okay, we're going to talk about polymer interactions with water a lot during the second half of the semester, but I'll just sort of introduce the concept here since we've been talking about interactions between polymer chains. Most polymers used for biomedical applications are in contact with water or some kind of aqueous environment, because our body is largely comprised of water. And so how does this affect polymers? Some polymers are not affected really at all. So polyethylene, for example, here, the most boring polymer that there are just carbons and hydrogens here. It's a very hydrophobic molecule. It's a very non-polar molecule. So it's pretty inert in the body. It's not going to interact with water too much. On the other hand, we can think about other polymers that have polar side groups here, even have polar elements to their backbones that can take up water. So again, water has got a structure like this, H2O, right? So water can form hydrogen bonds with oxygens here, this oxygen, and can associate with the polymer. So polymers that can take up a lot of water we call hydrogels. You've probably heard that term before. And some polymers, some hydrogels can swell and absorb up to 200 of their weight % water. One example is the polymer that is found in diapers, for example. It's a good thing. Just have a little bit of this powder in granules in disposable diapers can hold a lot of output from babies before it gets filled up. So polymers it's possible for polymers to absorb a lot of water when they've got these polar groups either on the backbone or in the side chains. And this particular polymer, polyhema, is used for contact lenses, and it can display actually hydrophilic or hydrophobic behavior depending on the environment that it's in. So they call some of these polymers smart polymers, where their properties are dependent on pH, they're dependent on temperature, and that sort of thing. And there are some cool functions and some cool applications that we'll talk about later in the semester associated with those. But it all goes back to thinking about the structure, looking at the structure of the polymer and being able to predict properties of that polymer based on its structure alone. And we can predict, if we see these polar groups in the backbone or on the side chains, the degree to which the polymer is capable of taking up water. So this slide has a lot of text on it. I'm not going to read through it, but I'll leave it in the slide deck so you can study that on your own, just summarizing the differences between thermoplastics and thermosets as different categories of polymers. Okay, I want to introduce this real quick and we'll pick it up next time. Two different ways that we can synthesize polymers. We call these addition synthesis or condensation synthesis. And as the names imply, names kind of imply how each of the synthesis methods works. Addition synthesis requires a monomer and a molecule called an initiator. And an initiator has a radical, it's a radical molecule, which means that it has one spare electron. So it's always looking, it's a very reactive molecule. It's looking to attack other molecules and bond with them, particularly molecules with double-double bonds, like a monomer. Monomer can have double-double or, monomer can have a double or a triple carbon-carbon bond right here. So addition synthesis involves monomer with a double or a triple bond and a radical molecule that we call an initiator. Condensation reaction requires two different monomers to come together. So here we've got dimethyl terephthalate and ethylene glycol. And when those two monomers come together and react, they form a polymer, they form a longer molecule, and they kick off some kind of side product. In the case of this reaction, they're kicking off a molecule of methanol. So the requirements for condensation polymer synthesis are that we've got two different monomers, and the monomers need to have two different functional groups on them. Okay. So just step through how we do a polymer synthesis with the addition reaction. We need this molecule called an initiator. So an initiator might look like this, kind of a symmetrical molecule. And if we apply some energy here, the initiator will split into two molecules that we call radical species. So it's going to split right here. And this bond is comprised of two electrons. And each of these molecules is going to get one electron. So this molecule right here, we call a radical species or a radical molecule, is very reactive, and it's looking to attack another bond somewhere else. So that's the initiation step when we form these radical species. The next step of the addition synthesis is takes up most of the reaction. We call it propagation. This is where we form the polymer chains. So what happens in this step is this radical molecule is going to, or this radical electron here, the spare electron is going to go and attack the carbon, where there's a carbon-carbon bond. And these electrons are going to get pushed out here. And this functional group, whatever it is, we call it R, just it can be any type of functional group. This R gets tagged on to the end of this ethylene molecule. This double bond has transformed to a single bond here in the middle. And we still have this one unpaired electron on our molecule, but now we have lengthened the chain. So this molecule can now, with its electron, sorry, should include that, can now go and find another ethylene monomer to attack. And when it does that, it's going to add to its chain length, and it's still going to have this extra electron. So this step, this propagation step, happens many, many times. If it happens 1,000 times, we can say the degree of polymerization, the dP, is 1,000. So this step happens many, many times, forming a very long polymer chain until the reaction terminates when two of these radical species find one another. And when two radical species find one another, they're very happy. These two spare electrons come together, which forms a single bond, right? We need two electrons for a single bond. And it forms this species here, which is stable because there are single bonds, there are no more radicals, and this would be a final product of the reaction. So you can see how we would end up with a distribution of different polymer molecular weights, depending on because it depends on when two radical species happen to find one another. They may find one another quickly when they are this length, or there may be many, many polymerization steps, many, many propagation steps that happen before radicals find one another. And then you have a polymer that's a very long chain length. So it's very difficult to say all the polymers are going to be exactly 1,000 monomers long. You always end up with a distribution because of the nature of this synthesis process. Okay, I'll stop there. Sorry, I'm a few minutes over time, but I will have office hours at noon if you have some questions. And we'll pick this up again on Wednesday, talking about other types of polymer synthesis.